everyone, my name is Saborno Isaac Berry from Berry Science Lab, and welcome back to Electromagnetism, lecture number 3. Last time, we finished going over the delta function, which is the last of the fundamentals we need to know in order to consider electromagnetism. Today, we're going to start studying physics, for real. So, what's the first concept we're going to study? Well, magnetism is considerably more confusing than electricity, which is why we're going to study electricity first in order to get a better feel for it. Also, you probably studied electricity a lot more in previous courses than magnetism, which is why it's also better to start with electricity. So, we're going to start not just with electricity, but with electrostatics. Now, can you predict what electrostatics is going to be about? Well, you probably can. Electro implies the existence of electric charges, and statics implies something that is at rest, not moving. So, electrostatics, when put together, means studying charges that don't move. More specifically, it's like taking a snapshot of an electrodynamical system, like a picture. And if you take a picture, you can totally disregard time as a variable because you've just taken one fixed point in time. Now, everything in a picture is static. It's not moving because time is at one constant value in electrostatics. So in electrostatics, we don't care about velocity or acceleration. All we care about is position. And with position comes force. What is that force dictated by? Well, it comes from Coulomb's law, which dictates that the electric force, much like the gravitational force, sorry, I should probably start writing in black again. So here, everything is all about the force. Now, what is the force? The electric force is very similar to the gravitational force. Now, what does the gravitational force tell us? This is Newton's universal law of gravity, and it tells us the gravitational force is g, a universal constant, multiplied by m, multiplied by one of the masses, multiplied by the other mass, multiplied by the radial vector, divided by r squared, where the radial vector is your distance from the source of the gravitational field. Actually, no, that's not what the radial vector represents. If the source of the field is here and you are here, then this vector from here, the center of the source to you, is the radial vector. If you normalize it, its magnitude is the radius, r, that you see here, and the normalized radial vector is this r hat that you see here. Hat usually denotes a unit vector. Okay, so how is Fe similar? Well, take a look. You have 1 over 4 pi epsilon naught. This is permittivity. Charge of one, charge of the other, radial vector over r squared. As you can see, both equations are pretty much the same with the constants looking slightly different. Now, Q, charge, is kind of like the cousin of mass, but in electrodynamics. You see, you probably already know that if something has a small mass, it exerts basically no gravitational field. Like me, I'm not attracting any of these cameras towards myself because the tripod has low mass, and I also have low mass, relatively speaking. And the bigger something gets, the more of a gravitational field it's going to exert. We'll talk about these weird arrows in a minute. Similar to that, charge is such that if you have something with very small charge, and no, charge has nothing to do with size, if you have something with very small charge, it's going to exert a relatively light electric field. Whereas if you have something with a large amount of charge, it's going to exert a much more dense electric field. The strength of the electric field is going to be stronger. But what is the electric field, actually? Well, the electric field is just the same formula, but without the charge of the source. So this is equal to, actually I should write this as Qs, and similarly this is Ms. So E is just 1 over 4 pi epsilon naught Q r hat over r squared. Alright, so that's interesting. The first thing you probably want to know is, what are these lines for real? Well, these are what we call field lines. Now, as I mentioned in the first lecture, the electric field is a vector field, but you can't draw all of the vectors of a vector field out. The same way you cannot draw all values of a scalar field out. If you assign a value to every point in space, there's no way you can fit all of them together without overlap. And overlap makes things confusing and unreadable. So we only draw a finite amount of vectors that are equally spaced. It's kind of an approximation of the field to show you its general feel, where it wants to go. But you might also ask, why am I drawing so few for the little charge and so many for the big charge? Well, that comes down to another problem. Diagrams like this can quickly become crowded, hard to read, and hard to calculate. Instead, we kind of cover them up with these curves. These are what we call the real, not field vectors, field lines. So these field lines are pretty much informal. There's no formal sense of them like the electric field vectors, which definitely have a formal form. These guys are just things that we draw to simplify the diagramming process of drawing an electric field. Now, what we do when we draw these conventionally is make the field lines denser if they have more strength. This way, because, these field lines are noticeably longer than these field vectors. But if we make them all into lines, you might start thinking, well, where has the strength gone? How are we going to tell that this die has any more charge than this? Well, there's a simple solution. Just draw more. And of course, as you draw more, they're going to spread out, which represents the electric field getting less dense as you get farther from the source, which reflects exactly this factor in the original equation. Now, one more thing. We're not always dealing with discrete electric charges. Sometimes we're dealing with volumes. And inside those volumes, we can have a variable charge density. Now, a charge density, just like you might have used the point mass model in Regent physics to represent mass sources or the gravitational field. But in reality, there is no such thing as a point mass. There are solids which have a certain amount of mass density inside them. The same way, there are surfaces with certain amounts of charge density. Remember, charge and mass are practically analogs in dynamics and electrodynamics inside them. Okay, so then this actually becomes more of an integral. It becomes an integral over the volume that we're taking. And next time, we're going to figure out how to actually take the integral of the electric field over the area. Why is that important? Well, you see, if you have, let's say, a bowl and a strain, you want to see how much water, if I have a faucet putting water into this bowl, you probably want to ask yourself, well, how much water is going through this surface per second? To solve that, you would have to find the water flux. And to actually do that, you need a bunch of stuff like Bernoulli's equation, but we're not here to talk about fluid dynamics today. Similarly, charges work almost like electric faucets. And sometimes you want to figure out how much of that charge is penetrating a surface per second. And that's what taking the integral of the electric field, and of course they don't actually disperse charge like that. They disperse an electric field, more like. And so you might want to ask yourself, well, how strong of an electric field are they giving or dispensing over this entire surface? And to do that, you have to take this integral. And we'll figure out how to take that integral, which leads to Gauss's first law, next time.